Started here. Welcome and thank you for joining us today for the Precision Dairy Farming from Hooves to Harvest webinar series. This project is brought to you by the UVM Extension Northwest Crops and Soils team and is sponsored by the Vermont Agency of Agriculture, Food and Markets. Oops. There we go. We have had a great lineup of speakers from all over the world over the past week and a half. And today we have two experts joining us who work with tools that are being used out in the field and to help with on-farm feed management. You can use the same Zoom link that was provided to you when you registered to access all of the sessions. And all of the sessions are being recorded and posted to the Northwest Crops and Soils program website under the Conferences and Events tab. So if you've missed any, you can find them there. There are water quality and certified crop advisor credits available for each of these sessions, and we'll share the link and QR code at the end of the session. And there will also be 3 poll questions throughout the presentation. So if you could take a second to answer them when they pop up on your screen, we would really appreciate it. And if you have any questions during the presentation, please enter them in the chat and we will facilitate them when the speaker has concluded. Our first speaker today is Chris Creek. He is the Northeast Region Manager for Precision Planting and is based in Pennsylvania. He has spent much of the last decade educating growers and industry professionals on the importance of the planter pass and proper way to maintain and prepare planters for the spring season. Recent developments have led him to become a student of the agronomic impacts of other equipment passes and the benefits and potential pitfalls of applying precision sensing, control, and even AI decision-making technologies to every field operation. Thanks for joining us today, Chris, and you can go ahead and share your screen. Looks good. You're on mute.
Is that a little better?
Yes, thank you.
All right, Amber, thank you. Thanks everyone for showing up here today. My name is Chris Creek. My role over the past decade or so has been primarily an educational one, but focused primarily on a different piece of equipment. Now, our company has recently begun focusing on sprayer pass, but you need to understand that I am very much a student of this technology. And the truth of the matter is the sprayer pass, as much as the planter pass is a very complex approach, the sprayer pass is far more complex. We're finding that it's not enough just to get the right rate out there, but the right pressure and the right droplet size and being able to do it in an effective manner. It brings in a whole nother level of complexity into an equipment pass. And in order to give you an idea of what's gotten us to where we are today, I'd like to start with a little bit of a history lesson. First of all, our company has always had an approach of identifying some kind of problem or issue in the field, something that was limiting the ability of the grower to do the best job possible. And once we identify that problem, our next approach was to develop some type of sensor technology, some type of ability to be able to measure and quantify exactly how big that problem was. What kind of impact is that problem making? What does this mean dollar-wise to a farmer? What does this mean productivity-wise to a farmer? And when we come across a problem that's making a big agronomic impact, that's impacting farmers in a way that's really hitting them in the wallet, at that point we develop a solution to try to address what that problem is. And on the planter, we've been able to introduce a lot of technologies that have kind of addressed some of those, and the planter has kind of informed our approach to the newer piece of equipment that we're being involved in as well. And so what we're trying to focus on is to recognize that there's a ton of things that matter in the field. Hundreds of things impact our ability to produce a crop, our ability to do so profitably and productively. And there's only so many things that happen all season long that we actually can take control of and make a change in. When I start talking to farmers about what are the things that matter, what are the things that impact your ability to raise a crop or to do so profitably, the weather comes up. Well, so far we're not able to control that. And so while it's important to know that that's going on, it's more important to focus on those things that we know that we can do something about. And that apology is going to extend here because I'm going to use a lot of analogies from the planter and I'll bring them over into the sprayer. I think you'll see how this picture's coming together as we progress. But we approached a planter with what we called a priority pyramid. There were certain things about the way that we placed seeds in the ground that made it more or less likely that those things were going to successfully express the genetic potential in the plant. And things like population and spacing, they're important, but they're not foundational. The things that are really foundational are being able to make sure that each and every seed has the best opportunity to grow and thrive. And essentially, it comes down to the uniformity of the crop. In an ideal situation, we would give every single seed exactly the same opportunity to express its maximum genetic potential. And as it turns out, that's a pretty common approach across agriculture. If you've got uniform genetics and we're able to give each and every one of those genetic organisms everything that it needs to express itself, we should have great results. And on the planter side, the first approach to this was a really, really simple one. We met a fellow by the name of Eugene Keaton, and Eugene recently passed away. But this guy was an agronomy engineer. At the time, he worked for John Deere, and he had actually developed a John Deere finger meter. But he identified that as we were dropping seeds into the ground, we were losing a lot of time because those seeds weren't effectively interacting with the soil. And he thought, well, what would happen if we took some type of device and pressed those seeds down into the soil and gave a much better seed to soil contact? What would we be able to do? And that eventually led to the development of what we call the Keaton seed firmer. It's just a simple little piece of plastic. In the beginning, we would zip tie them or we'd clamp them to a seed tube. And the job of this thing was just to push the seeds down into the furrow. But this opened up a relationship with Mr. Keaton, who was a consummate farmer. I mean, this guy was identifying all of these issues that we were trying to correct. And he desperately wanted to improve everything that he was doing. And because he had invented this finger meter, he and our founder worked together to try to improve that mechanism. And we worked together with a lot of different technologies. I mean, we took every type of technology at the time that we could, every type of sensing technology to try to identify what exactly is going on as these things are operating. And here you see an excerpt from a high-speed camera run. This is just one of the sensing technologies that we use to try to figure out, is this mechanism doing what it's supposed to be doing while it says it's doing it? And you see, we just had a seed bounce right out of that seed tube. We were learning things about the effectiveness of the equipment in the field. And back in those days, we certainly didn't have the ability to have the equipment make any decisions on its own. But one thing we did learn, and this was a quote that was stated by Grace Hopper, who was a Rear Admiral in the Navy, one accurate measurement is worth 1,000 expert opinions. For us, that's come down to this, I guess, basic premise or driving philosophy. And that is, you can't manage what you can't measure. You were talking about feed quality, and and dairy farms, oftentimes knowing what is your components of your manure, what are the components of your milk product, how is your ration being mixed and distributed. And unless you can measure these things, it's very difficult to really manage how they are impacting your operation. And so we became a student of these sensor technologies, and we developed a lot of different technologies. This is a This is a sensor mechanism, essentially a diagnostic tool that we use to try to test and see if meters are working correctly. And once we figured out if these meters are working correctly, then we could go ahead and make changes and see how those changes were being impacted in real time. And you need to remember that this is back in the day when the state-of-the-art technology was kind of a blinky light in the cab that told you whether or not a seed was being dropped. And so as we began to put more and more of these sensors on this equipment and began to get this feedback and start to analyze this data, it became more and more apparent that not only do we need this analysis equipment in the lab so we can learn in the lab, but it was really going to be necessary for us to have it in the tractor cab as well. And so we took that same technology that we were using on essentially these lab tools, and then we brought that same exact technology and we put it on the planter itself. We developed sensors that were able to measure what was going on the equipment in real time. And one of those sensors, just as an example, this is a downforce sensor. Nobody really thought before to measure the amount of force that was being carried on the gauge wheels of a planter. Well, how do you know if you're actually planting your seed at the depth that the planter's set at if you don't have a sensor to tell you if your gauge wheels are actually carrying weight? And to try to fast forward through this a little bit, once we had the sensor data to show us whether or not we were carrying weight and how much weight we were carrying, now we could start to analyze some of that information. We could start to see patterns and visualize what's going on. And understand that at the time, all we were able to do based on this data was to get out of the tractor cab, walk around to the equipment, and start to make adjustments based on what we were seeing. But as those systems got more and more intelligent, we got more and more information, we started to develop what would eventually be called artificial intelligence. You see, if we understand that there's a certain range of specification that we're comfortable with, and we can identify when our equipment is starting to get outside that range of specification, now we can put some automated tools onto the equipment, and we can start making adjustments in real time that are not informed just by an operator's decision, but are informed by a computer program that analyzes the data, analyzes the sensor inputs, and makes those changes in real time. And back in the day when we introduced this took that sensor and it married it to an airbag and an air compressor. And eventually we got to the point where we were able to replace all that technology with hydraulics that acted much more quickly, that were much more precise. And over the past several years, we've actually introduced 32 different sensor and response systems. And of course, we've updated all of the computer hardware and all of those things, and all of that to say this: there are a tremendous number of things that impact the crop in the field that happen as a result of just day-to-day equipment operation. The very nature of the way that the equipment works implements some kind of baseline in the field that gives us a limiting factor in the field. And it's kind of difficult to see here, but you can kind of see that there was a planter that came through here and took a bit of a curve. And if you look at the arc of that curve very close to us, you see those plants are very, very close together. And out toward the end of that, the plants are much further apart. Well, as it turns out, you can measure that as well. And as we were able to take a look and analyze some of those things, what we realized is when you're on a piece of equipment that's all being controlled at the same rate, if you vary at all from a straight path, you're going to start making rate changes on one side of that toolbar or another. In this case, you can see that we severely overpopulated the inside of that turn and severely underpopulated the outside of the turn. Well, the state of the art at that time was a hydraulic drive system that was essentially the same the whole way across, or you might have a couple of sections. And what we realized was, because of the losses that we experienced due to this variation across the machine, we needed to address that. And so when the state of the art was this kind of mechanism, we introduced a little 12-volt electric motor that attaches right to the metering device, row by row on the machine, that was able to give each and every row the ability to respond to what the needs were in that particular row. Well, you remember we talked about giving each and every plant the same opportunity for success as the one next to it. Well, that's pretty important when it comes to the population of any of these seed populations. Well, there are other variations as well. You can see here's just another example of this, but this is not actually a seeding population map. This is a liquid fertilizer application map. And you can see, because we're applying a liquid at a pressure through an orifice, we're changing the velocity, the forward motion of that planter bar, but it's not able to adapt that rate across the planter bar. And as a result, we over apply the inside and we under apply the outside. Well, in this case, we took what was the status quo in liquid application and we replaced that with an individual control as well. We called that vApply HD. Well, you can see as we're starting to get into liquid fertilizer application, now there's a possibility that there's an application for this technology across other pieces of equipment, because it's not just fertilizer systems and planters that have this issue. You can see this was actually an early demonstration we did of that vApply HD product. As this planting machine takes that turn, you can see that it adjusts the rate to try to adapt to that turn. And then as the planter straightens back out again, it adjusts the rate to make this even and uniform. And once again, this isn't rocket science. This isn't anything that any other company isn't able to see and do. But our unique approach is that we identify issues that are going on in the equipment. We use our sensor information to inform those decisions, and some of those decisions we're able to automate, so it takes it out of the hands of the operator. Well, this is all great. We've got all these sensors that are giving us information in the cab about what's going on. We're able to inform decisions in the cab, and we're even able to automate some decisions in the cab based on this information. But the problem is there remains another very large piece of variability in the whole planting system, and that's the soil. I mean, the soil varies inch by inch, yard by yard, acre by acre as we're planting in the field. And do you think that the variability in the soil has any bearing on the ability of that crop to be sustained? Well, absolutely it does. In fact, we've had all kinds of practices for soil sampling and soil testing to try to make different zones and variability ranges within the field to try to address some of that variability. But the truth of the matter is those technologies fall short. They're separated by time. They're separated. It's not always easy to get those layers of data to correlate. There's always problems with taking that information and applying it to these operating passes. And so we took a look at what we had going on. You remember this little piece of plastic that's dragging in the furrow? Well, we're a sensor company, right? What would happen if we put a sensor on that little piece of plastic and we were able to detect things about what was going on in the soil in real time? Would we be able to identify variabilities in the soil that would give us some insights that we could make some changes on an automated basis using computer-controlled artificial intelligence to make decisions about how to treat that inch of the field? Well, as it turns out, we developed a sensor, and we have been able to do that to a large extent. We're able to detect soil temperature, moisture in the furrow. We can detect if we've got enough moisture to germinate, or if that moisture is uniform in the furrow. We can even identify the difference between furrow residue and soil, and we can identify those issues in the field while we're planting. But the one that really helps us to make informed decisions, we're able to measure and monitor and map soil organic matter in real time. And this soil organic matter allows us to calculate CEC in real time as well. And without getting into a lot of detail, I don't want to make this into an agronomy course, but understand that soil organic matter and CEC, as those increase, that's an indicator that we've got a more productive soil. It's a better porosity, a better water infiltration rate, more ability of the nutrients to be passed from the soil to the crop, more ability to retain nutrients in the soil and have them there when we need it. So does it make sense that if we know what our organic matter is and we know what our CEC is in real time, and we're able to make real-time changes in the equipment, does it make sense that maybe we could apply that sensor data to some of the automated systems that we've already got on the machine, and we could make some fertility rate changes in real time based on the ability of that soil to hold and utilize that fertility? Can we make population changes in real time based on the soil's water holding capacity? Could it support a higher population of plants? In a lower organic matter soil, a less productive soil, does it make sense to reduce our rates so that we're not over applying in areas where we're not even going to be able to take advantage of those higher rates? So it's not just a cost saving feature, it is an optimizing and maximizing feature. And so this is what we've been doing on the planter for a long time. And in the process of all of this, we never stopped our research and our striving to understand exactly what the plants were doing in the field. In fact, what you're looking at here, we call this a pogo stick. And this is just a research tool that we've used. Essentially, it's got a digitizer on a tape measure, and it's got an iPad up on top that allows us to identify a growth stage of a plant and identify spacing and emergence. And essentially, it's a quantification tool. It speeds up the process of just analyzing a plant stand. And since we've developed that tool, we have cataloged over 20 million plants. I'd venture we're probably closer to 30 million plants that we've measured and identified and followed through to yield to see how all of these things are impacting. And in the process of this, we realized, well, we've got this great computer sitting on top of this pogo stick, and it's given us some really interesting information. But these computers that are on top of the pogo stick, they've got some interesting sensors on them as well. And these sensors are getting better and better. What's the likelihood that we could utilize some of these sensors that are already on these existing machines? Do you think maybe we could utilize the cameras and some of the tools that are already built inside these things and program some AI to be able to recognize some of these things in the field in real time? Well, we've developed that. This is a tool that we're hoping to release here very soon that we call Smart Scout. And you can see this is just a lab test of this technology, but this is that technology in use in the field this past spring. This is a field I was scouting at Penn State University. And you can see that it's looking down through all that residue. It is identifying corn plants. It's telling us what the growth stage of those plants are. And it's actually measuring the distance between them. It's identifying skips and multiples. And it's showing us if those plants were emerged properly. Well, I can tell you that the artificial intelligence that runs this, first of all, it doesn't rely on the iPad. Like we can use that of artificial intelligence with any camera system and apply that anywhere. It also doesn't have to be handheld. It doesn't have to be carried. And I can tell you that its ability to identify growth stages in corn is only because that's what we've educated it to this far. There's every reason to believe that we can identify just about any other type of plant in the field as well. And what would happen if we took that AI technology on a similar camera and we were able to apply that to a pass that you're already making over your field each and every time? You know that the planter covers the field once a year. In a good year, it only covers the field once a year. Most years that sprayer is covering the field several times a year. Some crops you could see that sprayer go over the crop 3, 4, 5 or more times in a season. And one of the most time-consuming things that a farmer has to do is scout his fields. Well, imagine you're able to do that scouting in real time while that sprayer is moving through the field with every single pass. We're there. The camera technologies we've developed, the artificial intelligence to recognize the plants in the growth stage, and we're teaching it what weeds look like. We're able to identify problem areas within the fields And that brings me to what those priority issues on the sprayer would be. Just like on the planter, we've got a priority in the sprayer to make sure that we're at an appropriate rate and we're timing at the right time. Making sure that we've got an appropriate droplet size and that we don't have skips or overlaps in what we're doing. And the problem is with a typical sprayer system, we have the same type of variances in turn rate that we identified in the planter. You could see if we're trying to hit a rate, we might be half rate or lower on the outer edge of the boom, and we might be double rate or even more than double rate on the inside of a boom. In fact, as the sprayer changes velocity within the field, which, I mean, it's one thing if you're in a couple of 100-acre field out in the Midwest, you probably don't have to slow down for telephone poles and for ditches and such very often. But here in the Northeast, we're having to slow down for such things all the time. And every time you do that, there's a small variation in pressure. There's a small variation in rate that takes place. And in fact, that variation in pressure, not only does it affect your ability to maintain a consistent rate, but it also affects your droplet size. As the pressures increase, you get a finer and finer droplet. And as the pressures drop, you get a coarser droplet. Well, the answer to this is PWM nozzle control. And the PWM just stands for pulse width modulation. Essentially, what we do is we set a target rate and a target pressure. And based on what the system is seeing at any given nozzle at any given time, it determines how much of that product it's going to let out the nozzle by controlling what percentage of the time that nozzle is actually open. So if it sees that it's got a 3-gallon flow at 100% and it needs a 1.5-gallon flow, all it needs to do is shut off half the time, and it's going to maintain its consistent pressure, but it'll maintain the rate that we need. And that's essentially what we've done. Once again, this is not a new technology. This is not something that was developed by Precision Planting. In fact, everybody here is probably familiar with a PWM nozzle control system. And this is an illustration of the problem, one of the problems that this corrects. With a typical system, as your speed changes, your pressure changes. And as your pressure changes, your rate changes and your droplet size changes. And you're trying to maintain something consistent. And all you can really do is hope for the best average. With a PWM control system, as you're starting out, your nozzles are able to make changes right at the nozzle level, and you're able to maintain a consistent rate, consistent pressure, consistent droplet size. In fact, the beautiful thing about a PWM nozzle system is it completely separates the rate decision from the pressure decision. You dial in the pressure to get the droplet size you want, and then the rate becomes independent of that, regardless of what speed you're applying. And this is a problem, not only in an over and under application of rate. Remember the turn problem that we showed you, the pressure problem that we showed you. This is not just a rate problem, but it's also a droplet size problem. In fact, some of the research that we're doing is showing that 40% or more of our applications are off-label. And think about this. Every time that we're going in excess of our labeled rate, we run the risk of plant injury, crop injury. And every time we're going less than our labeled rate, we're literally breeding resistance within our own fields. In fact, we're in the process of losing modes of action, losing chemistries and modes of action, simply because we've not been able to maintain consistent rate and a consistent kill. If you want to be the most responsible with the inputs that you've got, we need to maintain a very consistent kill. And pulse width modulation is one of those tools that allows us to do that. So this is a pulse width modulation system, but let's look back at that camera system that we told you about. What happens if we place that camera on the boom and we're able to identify what we're targeting while we're spraying? Does it make sense that we can be much more intelligent about exactly where we're putting that product? If we can identify not only where the weed pressure is, but how dramatic that weed pressure is, what growth stage those products are in, does it make sense that we can change not only our on or off, we can actually change rate to make sure that we're getting an effective kill. The beautiful thing about this is that we can apply the rate where we need it, just when we need it. And in addition to being much more effective, it usually ends up saving us a tremendous amount of money on product as well. And this is just another view of the same type of technology being used. Why in the world would you be spraying that product all over that nice clear field when where you really need it is just where you've got those outbreaks? And in addition, we can treat our systemic and our contact herbicides differently by using an injection system or a multiple tank system. This isn't where we are commercially today, but this ultimately is where things are going to head. Being able to apply a residual and also being able to target systemically right where we need it. That's where we're ultimately headed. And the cool thing is this artificial intelligence can do a lot of other things. It can not only can it scout our fields, not only can it identify weeds in the field, but it knows where the rows are. And the truth is, it's very, very difficult to steer a sprayer with just GPS, especially in an area like ours where we've got side hills and contours and all manner of things like this. I can tell you as a novice sprayer operator myself, when you hit the button and engage that camera-based steering system and it just hits the center of that row every time, that's a pretty amazing feeling. And once again, this is just an illustration of the system's ability to view that field, not just in a visible spectrum, but in a near infrared that is able to scout for nutrient deficiencies. It can scout for disease issues, also scout for weed issues. With every single pass that sprayer makes, it's able to make those determinations and identify that information. And pairing that with a tool like what we call Panorama, we're able to take that data, share that with say agronomists or people that are working on our farms, where we're seeing a high weed pressure area. Those are the areas that we want to take our time and pay attention to through the season. Why waste our time scouting a bunch of area where we don't have weed outbreaks and problems? We ought to just focus that time where we know we're going to have issues and where we know we need to go back later to check and make sure that we've been effective. And then we can also bring combine data into this or whatever harvester, silage harvester data. And we can start to identify yield by hybrid, yield by organic matter, yield by weed pressure, yield by rate application, all through these simple apps that allow us to evaluate what we're doing. And of course, being able to share that information with trusted advisors in the field. And so what I was hoping to do was give you an idea of the excitement that I've got for the vision system moving forward, for artificial intelligence applied to camera, equipment mounted cameras, being able to make real-time decisions in the cab to make sure that we're on the right rate at the right time in the right place. And that's all I have to share. But I see there's questions in the chat. Oh, that was from Susan.
Yeah, thank you, Chris. That was really, really cool. I am amazed by the number of moving parts in this technology. It always is really interesting how everything works together. I have kind of a low-tech question. The scouting cameras mounted on the sprayers and such, can they measure like product drift from like wind or changes. Like you could see the booms kind of like moving around, especially on our super uneven fields here in the
Yep.
Northeast. Um, do those scouting cameras track where the product actually lands?
Well, I can tell you that that those cameras do not, but I can also tell you that we are measuring and monitoring that information because it's incredibly important. One of the things that we hope to reduce dramatically with the pulse width modulation system, we call it Symphony, but there's lots of trade names for that. I mean, we're not the only one that produces one of those, and the truth is that every one of them works the same way. Those pulse width modulation systems, if they can separate that pressure decision from the rate decision, but we can maintain a consistent droplet size, the drift issue becomes much, much less. Now, wind is always a problem. I don't know that you're ever going to get, well, I suppose you could have an artificial intelligence system that would measure the wind on a given day and refuse to allow an operator to turn the key. You could do that. I don't know that our farmers want us to do that, but apart from that, I don't know that we can do that. What the system is more likely to do is to know what nozzles are on, know what pressure it's at, be able to calculate in real time what its droplet size looks like, be able to measure and monitor wind speed, and then pop up a warning in the cab that says you might want to reconsider today. You might want to find something less damaging to do to your farm today. And ultimately, I think it was apparent that all of this technology is leading to a fully autonomous system at some point. And I don't know if this looks like gigantic, great big 110-foot boom sprayers. The truth is, the only reason we run that massive equipment is so that we can multiply the efforts of a single human being, right? I think as we get artificial intelligence doing this, having this artificial intelligence operating on smaller, more cost-effective, less costly, less expensive, less scary equipment probably makes more sense. And at that point, I think that you do have a system that says, I'm registering this amount of wind and I'm registering this humidity, and yeah, I'm not going to operate in these conditions.
Now, is your company also working on using this scouting technology on other equipment like drones so that you have that information before you are putting a tractor on the field?
Yeah, the beautiful thing about the AI that we're developing is it is absolutely platform independent. I think their important step was putting the AI onto an iPad. If you can put that on an iPad and walk through a field and it's showing you in real time, it seems obvious to me that a drone, any type of autonomous vehicle, any equipment passed through the field. The sprayer makes a lot of sense because it's in the field so many times throughout the season. But yeah, absolutely, it could be drone applied as well.
Cool. This is super exciting. Jeff wants to know, when do you think the technology will be available commercially?
You will see the vision technology from my company this fall commercially available. It will probably not have all of the functions that I mentioned, but you will see the functionality released probably scouting first, followed by steering, followed by spot spray.
Awesome. All right. Well, thank you so much for your time, Chris. We really appreciate it.
Thanks for the opportunity to talk. I hope it was helpful.
Yeah. Um, our next speaker is Adam Durrin. He's the founder of Aurox, a dairy technology platform for measuring and optimizing forage inventories. He grew up on a small farm in He grew up in a small farm town in upstate New York, but did not get involved with agriculture until later in his career. His current focus is on leading the Aurox team to innovate digital technologies that help farms make better decisions. Before Aurox, he worked as a digital technology lead for Cargill, and prior to this, he led one of the first drone service programs in the country for engineering and surveying services. Thanks for joining us today, Adam.
Thanks for having me. Looking forward to share some insights and technologies that we have and some insights on how to use them. Can you see my screen okay?
Yep, it looks great, Adam.
Okay, perfect. So today we'll just be going over the drone technologies and kind of secondary technologies to be able to use to optimize forage inventories and some of the questions and answers we can get from that. So why measure forages? Obviously, you know, I think it's pretty self-explanatory. And I promise you, I didn't just enter this quote in there. That happens to be exactly the same as yours. It seems to be a common trend among technology companies, especially in the ag industry. But really, I mean, you can't measure what you don't measure. You can't manage what you don't measure. So forages are a massive operating cost of a farm. I'm sure you're all familiar with the graphic on the left, showing just the percentage of costs associated with feed for a dairy farm. For farms over 500 cows, that's 58% of total costs. So we have, you know, in any type of business or operation in which inventory is a significant part of costs and labor and time and decision making, it's really important that you have high quality, accurate data to make decisions around that information, around that high cost, high value inventory. And not only that, but within dairy, of course, we can lose up to 20% of that feed due to shrink. So even more of an important reason to get a good value on that feed, to start tracking what that is, to be able to make some decisions to try to minimize that as much as possible. Because with the values that we're talking about with this feed on an annual basis, millions of dollars of feed, just saving a few percentage can be thousands of dollars of savings. It can be, and also have impacts on your nutrition, on the production of the cows. There's so many connected elements here that it's just such an important piece, and really why we need to have good data for this. And ultimately, just these small decisions, just these decisions around what we're doing with our inventories, how long they're going to last us, what we're going to do with our harvest, where we're going to place them. These small decisions and having data that you can actually back up those decisions and be confident about them can result in significant saving opportunities. Now let's of course get into why this new technology is so much better, and I mean it's pretty self-explanatory when you look at the old methods. Whether you're walking around with a measuring wheel or going up to the face of a pile with a probe, it's not very safe to do that. It takes a lot of time, and quite frankly, it's not very accurate. Even if it wasn't. Even if it was safe and you're getting this information, the amount of time it takes to do it, and because of the inaccuracy, it's not even really worth it to get that consistent measurements of the forage inventory. So I understand why in the past traditional methods, maybe forages weren't that much of a priority of understanding what is there, how much you have, how much you're using, and so forth. But with our new methods using drone technologies and a couple of secondary technologies, we can get extremely accurate measurements of the volume on the farm and the density as well. It's very safe, and it can be completed within 10 minutes. So very, very efficient, and allows you to get continual data over time. Now, on the right, you'll see a couple pictures, one from a 3D model, and the next of the actual measurement of that 3D model of the ground level view, and then kind of like a 45-degree angle. That ground level view is just kind of like, okay, you're on the farm. Let's imagine you're measuring that in the old ways, and then we hear this a lot with especially farms that have bunks. It's like, okay, we know how big our bunk is. It's got 10 feet walls, it's so many feet back, so we're pretty confident what's in there. But there's still a lot of variation and a lot that you can't be seen from the ground or even just kind of measured with kind of napkin math. In just this example here, when you split that bunk right down the middle, there's 35% more feed just on the left side of that bunk than on the right side of the bunk. So of course, piles, those are really difficult, but even within bunks, there's a lot of variation, and there's a lot of, we can get much more accurate with this drone technology. So basics to capturing this data. There's a few technologies that are really critical here. First is a professional drone, or at minimum, kind of like a prosumer drone, they're called. Then there's the positioning technology that can be either ground control points or real-time kinetic, and then the processing and measurement software. So related to the drone, there's a lot of kind of different combinations you can use. But the best accuracy you're going to get with the ground control points, and that's using these two high-end level GPS units, one as a base, one as a rover, and getting accurate points around the site that we can then correlate within our 3D model to make sure everything is scaled and sized correctly. The second piece of technology outside of ground control points, which is more efficient, it's not as accurate, but it's still much more accurate than without it, is RTK, in which one of those GPS units are on the drone. And it's geotagging very accurately the location, the precise location and elevation of those images, so that they get you much more accurate. And then with the processing and measurement software, it's really important to have the right tools so that you can measure the kind of unique scenarios that can happen on the dairy farm. It's very important to note that just because you have a drone taking images, and that creates a pretty 3D model, and you can click around in some off-the-shelf software to make measurements, that does not mean that's accurate. It's really important to have these technologies and have the control within the software to allow you to get accurate measurements. So the accurate positioning data, that's related to those ground control points I just spoke about, or the RTK. So without that positioning data, you end up getting models that are shifted, rotated, warped, or not properly scaled. So that when you're going in there and making measurements, it could be that the pile or feed is bigger or smaller than it actually is in real life, or it creates that shift or that rotation in which the plane in which you're making a measurement is not representative of what's actually there. The second issue is that those models aren't perfectly aligned, which means that every time you have to make a measurement, it's going to create new error because you have to create a new measurement every time. You can't measure exactly the same spot, the same pile, the same ground underneath that pile to get an accurate measurement. And that's why having the accurate positioning data with a software that allows you to match those two up is super critical here, especially if you're looking for more than just general inventories, if you're looking to get into a shrink or density or forecasting. Because that positioning data allows us to perfectly, or almost perfectly, scale those models and align those models so that you're getting accurate measurements and you're getting consistent measurements from flight to flight. So it's just some unique kind of situations that we've solved for within our software in dairy. There's a lot of kind of cases of joined piles or joined feeds in which they're bumped together, they're overlaid, or bunks with sloped floors, trenches with uneven walls, snow-covered tires. There's a lot of kind of factors in here that are pretty unique to specifically measuring forages at dairy farms. And fortunately, we've worked pretty hard to solve for all of these within our measurement software. But it's just kind of just something to look out for to make sure that if you're getting these results, or if you're working with some type of software that they may not be able to provide these types of measurements even beyond just the limitations within the accuracies and scaling the models to best represent the ground underneath those bunks or those uneven slopes and so forth. Now, understanding these results. So the technologies I just described gives you a very accurate volume, and that's only half the equation. Of course, volume times density, that's where we get our mass. So without density, we can still get very valuable information. We can still get a very accurate volume measurement of the forages on farm. And then if we use an industry standard or assumed density, we can still get just total general inventories. It's still going to be at least 50% more accurate than if you were doing it kind of the traditional ways. And we can start calculating those forecasts. We can just give you total inventory But if you really want to get very accurate, the total inventory and get into things kind of more in a precise method, then it's really important to measure that density. And we can do that here with this technology without having to go probe the bunk. And there's two ways of doing that. One is to use the load data from the feed software. And essentially what we're doing is we're just comparing the volume disappearance with the total tons used of that individual pile. And then we can calculate the density of that feed being used. The second is to use the scale weights from harvest as if the farm has its scales as they're going to pack the feed, then we can take that total tonnage and compare that to the volume. Now, comparing these two densities, we found it best to use the option 1. That's going to give you a much better representation of what ends up being there within the pile. Because using option 2, there's a lot of shrink, there's a lot of variables that happen within that process. And so sometimes those values don't exactly match up. And what that is mostly shrink. And so if you're looking for true inventory values, it's best to use method number 1. So like I said, density is half the equation. Super important metric if you were looking at inventories, if you're doing forecasts, and we want all that as accurate as possible. But also density in of itself is an important metric just to understand and to track, mainly because it's correlation to potential shrink within the pile. The higher the density, generally the less shrink that's going to occur. And so it's really good to understand what your densities are and to see how those densities can be improved. So the way that we measure densities, you'll see on that image there is what we can do is measure that in segments. It doesn't have to be in segments. It could just be after the entire pile is used. But once every flight that occurs, we're comparing that to our used volume. And then we create an average weighted density, essentially taking the proportion of volume versus the density calculation. And then by at least halfway through the pile, if the pile is fairly uniform, we should have a very good representation of what the density is throughout that entire pile. And then, of course, once the entire pile is gone, we can calculate that average density across the entire pile and have a very good representation of the total feed that was there. And again, it's very important to really highlight the technology, the positioning technology, and the right software is needed for this, because just small variations within those measurements can really provide misleading data related to the density and the overall inventory. And just comparing that to kind of the traditional method, we think that this gives a much better overall view, overall density of the bunk, rather than taking the probes of maybe one portion of the face. It may not be the best representation. Of course, it isn't very safe. We want to avoid that guy in the top right, going right up to the face and doing that, as much as possible when we can. So once we have the total inventory, we can start kind of making some decisions or thinking about how we're going to use the data. So this is kind of the cycle of our forage management in terms of how we can use this data. So we start with our total inventory, and then we can start running forecasts, understanding when we're going to run the feeds, and how much feed we have just to begin with, and how long that's going to last us. Then we can get into optimizing current inventory and potential purchases. Maybe we need to increase feeding, maybe we need to decrease feeding, maybe we need to make space for some new feed, and that gets us into our planning and layout of what we're doing with that feed. So, making sure that we don't have last year's crop stuck in the back of the bunk that's just going to sit there until the next feed is going to be used, making sure that we have enough space to put that feed, that we have the right dimensions to create a safe pile, a good pile. And then it's just kind of very next high level planning for the next year's harvest. So once we have total inventory, then we can start doing forecasting. Within our platform, there's two ways to do forecasting. One is to use our historic usage forecasting. That's essentially saying if you have 2 or more flights, how much is used during that period of time, and it automatically creates a forecast based on that usage. And that just gets you into some basic questions of, do we have enough feed? When will corn silage run out? When will this bunk be empty? What do we have right now, and what is that going to get us? The next step is to do the scenario-based forecasting. So this is where you can say, we need to increase the feed for this pile, decrease the feed for this pile. maybe we need this bunk empty by August. What do we have to do to make that happen so that we don't have that feed stuck in the back? Or even getting into the nutrition element of it and saying, we have multiple of these feeds transitioning in spring. What can we do? Kind of looking ahead to mitigate that stress to the cows. So the forecast in the platform, we can do. You can create custom forecasts even just with one flight. Let's say you do end of year total inventory, and then you can plug in your own values for your usages and calculate out those forecasts. But then, of course, having more data to create those forecasts over time is super beneficial. So now that we have our understanding of how much feed we have and when we're going to run out of that feed, then we can get into pile and bunk planning. So within the platform right now, you can make some kind of basic measurements, kind of like the traditional way, but of course more accurate and much less time consuming, saying this is the area that we have. Let's say, add a certain height of the pile and just do a basic calculation of what a pile could be or a bunk within that location. Coming soon, we'll have a feature in which you can actually visualize, you can place a pile or a bunk onto the site and scale that and resize that with the appropriate dimensions, the appropriate slopes, and know exactly, well, close to how much tons you could fit there, also knowing the ideal pile dimensions of what should be placed there. And of course, I mentioned this a couple of times before, but these are some of those decisions that can really help in the long term of making sure that you have sufficient space, you're not wasting feed, you're not moving feed around when it doesn't need to be. And even getting into, should we make some investments for feed pad expansion, make some more area here, add in some more bunks, and just getting into some kind of high level decisions around what you're doing with the area in which you're feeding. Now, of course, when we have consistent data over time, we can start identifying some discrepancies or trends within the data. So first, that could be just identifying some kind of anomalies within the data or some spikes or dips within usages, something that is sticking out that you may not have observed in your management or may not have showed up in the load data, and identifying those things before it's too late. This often happens with feeder errors, in which, let's say, a feeder is feeding from two haylage piles at once. In the load software, it's showing the appropriate amounts for each one of those haylages. But what's actually happening is he's overfeeding one pile and underfeeding the other. It's just being recorded as the appropriate tonnages for each pile. And so very quickly, we can identify that when we're comparing that to volume, because we're seeing far more volume being used for one of the piles, far less volume being the other piles. And what this usually appears as a super high density, like a 70 pound per cubic foot for one pile, and then maybe a 30 for the other. And it's like, these aren't realistic. This is probably because too much feed is being attributed and too little feed is being attributed from the other pile. So there's a lot of kind of things that you can identify here before it's too late, before all of a sudden, wait, we don't have enough feed for this, or even just looking back and saying, this probably attributed a lot of shrink or a lot of cost to our operation. Putting a value amount to that, and then being able to make some decisions. Okay, maybe these are some additional training we need to do. These are some additional investments we need to do to mitigate those happening in the future. Another level of data we can measure is shrink. So a couple forms here. Shrink is a very encompassing term. One that we're more confident about is the fermentation shrink, and the way that we're measuring that is essentially the percentage change in volume from right after packing to right before opening. Now, it's important to note that this isn't, of course, direct shrink. There's a couple other factors within there, like settling or maybe off-gassing or something. But we believe it's a good correlation to shrink, and at least gives you a good value to compare against others, to compare against yourself from pile to pile, from year to year, and help you make some decisions of maybe there's some things that we need to do to try to limit this or try to minimize this value as much as possible, and at least gives you some indicator to see how those decisions are taking effect. The ensiling shrink, I don't know if this is the best term for it, but this is something that we've started looking more into recently, and that's essentially taking, if the farm has those scales as they're bringing that feed from harvest to packing, to compare that ton value against the drone tons with a calculated average density, understanding what that difference is and what that kind of shrink between those two, that delta is between those two values. We performed a shrink study over the last year or so, looking at 3 farms in the Midwest of corn silage and then 1 haylage pile. The results we were pretty positive about, because there was a pretty high correlation between each one of the piles. You can see here that, I mean, and I think this is understood within the industry, that most of the shrink happens within that first month or so. So you'll see in that first 30 to 40 days, that most amount of shrink with the shortest amount of time occurs. But something very interesting here is that if you look at where those little X marks are, that's when the old feed was butted up against the new feed, and they started to transition into that new feed. And there's another kind of secondary spike of shrink right there. That was one of the kind of limiting factors of this study, is that we didn't have standalone corn silage piles to just study that. So it introduces some variables that we didn't want, but potentially kind of showed us or indicated or maybe confirmed that that may not be best practice to do, and maybe it's better to have a standalone pile. The small haylage pile, of course, it's hard to compare a small haylage versus a big corn silage pile, but the small haylage pile was a standalone pile, very small, used very quickly once it was opened, but there wasn't that secondary level of shrink in that. So some other uses of drones on dairy farms. Most of these things are things that we can do. They're just kind of slightly different applications of the software in which we're using to measure forages. Just like manure pit capacity, instead of measuring a volume, we're measuring what doesn't exist. So that can be done. Calculating tire and cover needs, basic calculation of the 3D surface area. Forage and site evaluation in the hands of a nutritionist or someone that really knows their stuff. It provides a nice tool for them to be able to go into that 3D model, kind of make some measurements, observe maybe they didn't do a good job of covering, maybe there's a lot of spoiled feed, looking at the face management. The 3D model is a pretty unique tool to be able to go in there and just remotely and safely and efficiently see a lot of things that are happening within that area. Pile dimensions for safety and planning. I've talked a lot about the planning already, but safety, of course, is a big important thing here, and making sure that that the farms are making those piles or bunks in a safe manner, and just being able to confirm that, and then perhaps recommend in the future, let's try to reduce that slope a little bit. Measuring exposed face surface area, doing field mapping. These are kind of more extended applications, but all completely possible with the drone. And then, if you want to just fly the drone and do some monitoring of if there's pastured cows or general site management, farm management, and then also getting into measurements for potential expansions, new barns, layouts, and so forth. If having a map or a 3D model of the entire site can be very helpful in those situations. So that gets me to the end. Just want to say thanks again for the opportunity to go over some of these technologies and some of the solutions, and open to any questions that you have.
Super. Thank you so much, Adam. If anyone has questions, they can put them in the chat. I don't see any right off here. I've got a few. You were talking about measuring shrink, and I was wondering how can you or do you account for feed waste from spoilage when you're doing your forecasting models, or is that just all considered in that shrink? Is it all part of shrink? Whether, if you're shoveling 6 or 8 inches off the top of your bunk as you're feeding it, is that a measurable thing with your technology as well?
It is to an extent. So we do automatically take out the physical shrink of the volume of the unused pile. So that's automatically factored out of the calculation. Now the actual spoiled or moved feed in those situations, that's a little more challenging, because once that feed has been taken out of the pile, we don't know the density, and we can't apply the same density as the rest of the pile to that. We can certainly measure the volume if it's visible and if that's seen, but that is something that we don't have the ability to see what of that is taken out of that pile, unless it's just like, you know, a little side pile of spoiled feed that they've set aside. We can absolutely measure those as well. It's just that then the question is, okay, what density do we use for that value?
You could still, like, you would have to calculate a density of just a sitting pile, right? Like,
Right.
yeah, it gets a little tricky, but doable.
Mhm.
Sounds like that's cool. And what's the range of shrink that you see? I guess I've always kind of heard it's like between 10 and 15%, but from the graph that you showed with the trial data, it looked like maybe it was lower than that. And is there a big difference in shrink between corn silage and hay silage?
So we haven't looked at shrink on too many haylages. But yes, I'd say from around 8 to 15% is what we've seen a lot. More so in the 8 to 12, I think, because those are very well managed and the farms have done fairly well with their piles. It's something that we plan on studying some more. It's not something that we're doing on a large scale right now, just because it's not a common request or interest. But it is something that we're starting to look into more, and we'll hopefully have better kind of like generalized results per region, farm size, different types of feed and things like that. But yeah, it's kind of dependent on individual farms.
Gotcha. And one last question. It's a little off topic. But is there drone technology, or is it coming to use similar to the technology that you're using to determine dry matter of pasture for grazing planning, like pre-grazing versus post-grazing? Like, is that out there and happening that you know of?
Quite honestly, I'm not too educated on that element of application. I've heard some speak talking in the past of using drones for that application, but from what I understood, it just wasn't very accurate. It just wasn't accurate enough to get actual data. But that could have changed, and I'm sure, you know, in the future there's certainly opportunity. I just don't know enough about it to give you a good answer.
Okay, I thought I'd try anyway. All right, well, that wraps up our presentation for today. Trying to share the QR credits or the QR codes here. All right, I think that's up there. Thanks for joining us for these presentations today, and thanks Adam and Chris so much for your time. We really appreciate it. There's one final session in this series, so we hope to see you back here on Monday to hear about precision weed management. Thanks so much and have a great day.
Thanks very much. Bye.
Thank you.